So I just unmuted all the attendees. Feel free to I enabled to unmute for all attendees. Whenever you have any question, feel free to raise your question. I like this session to be interactive. So for the first few, maybe 10 to 20 minutes, I will talk about the design for a scalable and high throughput concurrent metadata service, addressing this issue using different open source technology. So this presentation will take maybe 10 to 15 or 20 minutes. And after that, and we can just talk about how we can, if you have any questions, I like to hear from you, reporting issues, or talk about your proposal to our project. I'm happy to discuss with you. Okay, let's start. So my name is Bin. I am one of the most earlier members joining this project, and I'm the founding engineer of Luxio as company, and also I'm the open source committer for this project. And before I joined Alluxio, I was working in Google in building the next generation of the large scale storage systems. So this is me, and you have my email here. So today I'm going to talk about Alluxio and especially the metadata service of Alluxio. If you don't know Alluxio, this is an open source data orchestration layer for big data and machine learning data stack. It was originally a research project in UC Berkeley MPlab, known as Tachyon. In the early days, people built Tachyon as the off-heap in-memory block storage for Spark. But later on, we open source this project and also make it more general purpose file system. Instead of just serving Spark, it can talk to different applications, including Presto, Flink, MapReduce, Hive, HBase, or Caffe, or TensorFlow, using different APIs, including Java File System API, the HDFS API, and S3 or POSIX APIs. And one of the interesting perspective of Luxio in the data stack, it's also building a data abstraction on top of persistent data storage. So Alluxio has its own adapters talking to HDFS, Swift, S3, GCS, or some other file systems or object stores, but providing a unified and consistent logical file system to the applications. In this way, application developers and also maintainers, they have an easier job to manage the data, manage the life cycle of the data, but also being able to set data policies, including setting TTLs, caching data, doing data transformation, things like this. Alluxio has been open sourced for more than 5 years, has been deployed at large scale, more than like 1,000 nodes in companies like Walmart, Tencent, and many other companies. So this is like a very high level overview for what Alluxio is. But today I'm going to talk about, for this presentation, I would like to talk about some detailed design and implementation into Alluxio different components. First of all, I want to give an overview for the architecture if people are not familiar with what Alluxio is and how it's designed. If you're familiar with HDFS, the architecture, I would say, on the left-hand side is very similar to what HDFS is doing. You have the metadata service, which is called master, and we can have multiple different masters. You have master and standby masters coordinated using Zookeeper or embedded RAFT service. And master is responsible for serving the metadata, which is representing the file system semantics. You have directory abstractions of data on top of directories, files, users, groups, this concept. So these are called metadata. But to read the file, you need to go to the data. You need to get access to the data. and the data is distributed across different workers and served by the workers. So the way it works is the application needs to embed a Alluxio client, and with this client, you can talk to Alluxio worker and also different Alluxio workers and Alluxio masters. So that's in a high level how Alluxio stores the metadata and the data. But one unique perspective of Alluxio compared to other storage like HDFS is it has the concept of under storage. For the under storage, you can think that's the part on the right-hand side, that's the under storage. That's the source of truth for the data, and that's the persistent storage for Alluxio. Alluxio by itself does not provide data persistency, meaning it's a data abstraction. It provides different data strategies, different data policies, but you cannot persist data using Alluxio. It's a layer on top of other persistent storage. So you can mount, we have the concept of mount, you can mount S3 or mount HDFS into Alluxio logical namespace. And then the data writing to Alluxio with certain write type will be persisted into this under storage layer. And you can have different write policies to decide how would you like to have this data persisted in the synchronous manner or in the asynchronous manner. Okay, so for today's presentation, I want to focus a little more on the master, which is responsible for storing and serving the metadata in Alluxio. So when I'm talking about the metadata, I mean the data structure of the file system tree, representing the namespace, the logical file system namespace. So users can mount different files, other persistent file systems into this namespace. So the mounting and bring in the external data namespace is considered part of this metadata. It's part in the file system land. It's called inode tree. It's part of the inode tree. So we see, especially in the recent years, people are using Alluxio for having a lot of files because they are mounting maybe object stores to Alluxio, and which is responsible, you typically used for a lot of small files for machine learning workloads. And this is the inode tree is part of the data structure. And the other data structure is a mapping from files to blocks and their locations. And this can be very dynamic in Alluxio because you can think many people use Alluxio as a caching file system, and where to cache the data heavily depends on the workload dynamics. So it's possible at time zero, you have one worker caching the data, but later on, a lot of different applications are requesting a same data block. So that same data block can be cached into many different Alluxio workers. That requires you to change the structure of this file block mapping. And also another part is for this metadata is really understanding which one is the primary master. If you're running in the high availability mode, you may have multiple different masters. So in the design of Alluxio, we have one primary and with several standby masters. And we use, as I mentioned, the Zookeeper or RAFT to maintain this piece of information, which one is the primary master. So I'm talking about a few challenges we see when we are building this system, especially related to the serving and storing the file system metadata. The first problem is storing the raw metadata becomes a problem if you have a lot of files. And we do see people mounting large file system namespace into Luxio with more than a few hundred millions files or directories. Why this is a problem for Alluxio? So Alluxio is implemented in Java. It's a JVM-based project. And in JVM, to store the information for a file, including the file name, including the parents or the children directories information, or about their, for example, the permissions, each file takes roughly about 1 kilobytes on-heap memory in JVM. So if you have a 1 billion file, it will take 1 terabyte heap space, which is a lot. Or like 1 billion files may be exaggeration, but in reality, we do see people can reach to maybe 100 million files. That means 100 GB of heap space. And JVM typically is not without without modification customization. A JVM is not good at handling that large amount of heap space. So in that case, the GC can be a big problem using a large heap space. That means you will see a lot of performance issues because the GC is kicking very frequently. So that's one of the challenges if you store all the files, the file information on heap. But remember, on the other side, if you put a lot of files, if you're serving the files directly from JVM heap memory, that means it's pretty performed. That's very fast without GV kicked in. So that's the trade-off you have to make. How do you balance performance and storage efficiency? So another part is the metadata serving challenge. We're building a file system. There are common file operations. For example, list status, get a status for a file, or list the status for a directory. These kind of operations is very frequent for a lot of applications like machine learning analytics. Typically, the first thing they do is to list the entire input directory. So we need to handle this well because this is the common code path for a lot of different applications. And also typically you see a lot of different concurrent operations on this. So the next question is how do you sustain a high load? For example, if you have a cluster of 100 machines, because each client, on each machine, you may have one or multiple different Alluxio clients, and inside each client, you may maintain, by default, it maintains a pool of clients, different connections to the Alluxio master, the service. So you have to design this well so that we can handle high concurrent. And we know like users running Alluxio with more than 1,000 or a few thousands clients at the same time, then we need on the metadata storage side, it really needs to handle well on a high number of concurrent connections. Also, the life cycle for the connections needs to be managed well. For example, the TCP connection handshake can be expensive, and also if you're consuming some resource for even the idle connection, that's a waste of resource on your master, which can be quite expensive. So let's talk about how we serve the metadata first, how we handle the on-heap storage challenge using RocksDB. Basically, the goal for this iteration is to build a single node metadata storage, being able to store and serve more than 1 billion files in a single logical namespace. And the way we are achieving this is to build a tiered metadata storage. Some part of the data will be in memory, in heap, on heap, cached on heap. And the entirety of this data structure will be encoded into RocksDB. I will talk about RocksDB in the next slide. But essentially, we divided the data structures into different components. And for the RocksDB part, it's on disk, it's persistent on the local disk. And to store the inode tree, to store the block map, and also the worker block locations. But on the JVM side, we also maintain the inode cache for the most frequently used inodes, and also the mount table and the logs to make sure we still have a concurrent and high performance inode tree service. So RocksDB is an embedded persistent key value store for fast storage, originated from Facebook. And we used its Java binding to embed this open source library into Alluxio master. So the challenge here is to how we can abstract the metadata storage layer. And we tried different ways, and we end up with the design of the embedding this metadata inode tree using two different tables. I won't go to the details, but essentially there will be two type of tables. One is representing the inode to to its own metadata information called inode table. The other one is representing the connection information. It's basically it's encoding the edge table, encoding an inode to all its children nodes. So this two table solution provides a pretty good balance between performance and also common operations. You can achieve one lookup for listing using what is provided in RocksDB called prefix scan, and also for the path steps lookups, it's on order of ON. N is the depth of this tree, and also there's constant number of inserts for updates, deletes, and creates. So it's pretty good balance between the common operations and also the less common operations in terms of time complexity. So we can put Alluxio, the entire inode tree, into RocksDB and store that and serve that from disk. That's no problem. But you will also have a performance hit. So that's why I mentioned we have an inode cache. And in general, by default, you can cache about 10 million inodes, which is pretty good. It's a very large already for most of the use cases. And this can have this performance back to the performance where we storing all the inodes on heap in Java JVM heap memory. And also we can buffer the writes in the cache and asynchronous buffered to RocksDB. So this is really helps a lot on certain operations, modifying the inode trees like creating a table or delete a table. So essentially, by having by having this entire inode tree encoded in two tables stored in the RocksDB, but also maintaining a in-memory cache, inode cache on heap, it provides a pretty good balance between the cost, the storage, and the performance. So that's so much for the inode cache and inode tree using RocksDB. Next, I'm talking about using self-managed quorum leadership election and journal fault tolerance to provide high availability. So Alluxio masters, you can run Luxio master as a single master mode. That means you have no fault tolerance. Once the master is down, that is the single point of failure, and you will just lose all the information until the master is brought back. So you can also run Alluxio with multiple different masters to provide you fault tolerance. And traditionally, or like before Alluxio 2.0, we're providing a way to use Zookeeper using Zookeeper to coordinate between different masters. So you can use masters using the Zookeeper to tell which one is the leader master. And it has certain problems we see in for certain users. For example, their Zookeeper are oversubscribed. But also it requires, so running in this way also requires a shared storage for journal. Journal is basically the snapshot. You can think journal as a snapshot for the file system metadata information. So every time you modify the file system, there will be an edit log written into this journal. And this is persisted so that the next time you restart, if the class goes down or you restart cluster, you can go back from the previous state. That's called journal. So if you're using Zookeeper, then the journal is required to be stored in some shared storage. And in practice, many people use, for example, HDFS as a shared storage. But we know a lot of users nowadays are running Alluxio in the hybrid cases. They're running this in, for example, S3. And in S3, the journal storage will be a big problem because streaming writing to S3 is going to be pretty bad. The performance will be pretty bad if you appending object. So that is not available as an option. So we decided to build a self-managed quorum to store this journal, but also to coordinate among masters. So we pick RAFT as the protocol for different masters to communicate with each other. And the implementation we use is a third-party library called Copycat. It's a Java-based implementation for RAFT. So this is what we end up with. You can run multiple different masters as I show here. It's the leading master and multiple different standby masters. And every time if you read, so all the requests goes to the leading master if the leading master is active. And every change you're making to the file system, for example, if you're adding a new file to this file system or you're deleting an existing file from this file system, this is considered as a file system mutation. And that requires this leading master to make a commit among different masters. And then you can, we can rely on the underlying RAFT protocol. So the leading master can coordinate with the standby masters using RAFT protocol to commit this change. In a case, as long as you have less than two, n divided by 2 masters still lost, then this information will be still available and everyone can be on the same page because there's consensus among these masters as long as they reach the quorum. And another benefit is we can leverage the local disk to store the journal rather than requiring another external third-party shared storage. So we have done a lot of to tune the performance of running this the quorum self-quorum based metadata service. So the last part I'm talking about today is our latest transition from in the RPC framework from thrift to gRPC, and the lessons and why we're doing this. In Alluxio 1.x, we're building the RPC systems using 2 different protocols. One is using thrift. Thrift is an open source technology developed by Facebook, and it's actually very easy to use, and it's pretty easy to learn. And documentation is good. The problem is it's not supporting, at least the open source version, it's not supporting streaming IO operations. If you want to have a very short and quick control messages using thrift, that is actually the best fit. But if you have a big chunk of data to transfer, using thrift is not the best choice. So we decided in early version, we decided to build our own transportation layer using a netty. Netty is another event-driven Java-based network library. So you can think of netty as a very, very low-level programming library. It almost feels like you are operating on the socket. So it's very efficient in that way because the overhead is very little. But also writing a netty server and client is not I was involved in the job for Alluxio, and I don't appreciate that experience. It's very low level. It's very hard to extend to, and to be worse, because we have 2 different systems. One is using thrift, one is using thrift for the control panel, and using netty for the data panel. And the combination makes this very hard to maintain. Every time we will want to extend something, it's likely we end up with writing this twice, once in thrift and once in netty. So very hard to maintain and very hard to extend. And thrift is not maintained no more, and no streaming RPC supported. So that's why we decided, okay, it's time to go with one single unified RPC system. So that's why we choose our gRPC, which is the open source high performance RPC framework maintained by Google, and it works pretty well with protobuf for serialization, which we're already using anyway. So after that, we unified all the RPC interfaces using a single framework gRPC, and we can build the data transportation between client and worker using the streaming IO RPC, and we can use the non-streaming fashion of gRPC to communicate between client and master. And also we can have protobuf everywhere, and this library is pretty well maintained and very well documented. We have a lot of challenges in performance tuning I will talk about later. So the gRPC transport layer offers a few very good features. One thing I talked about previously is the challenge, as a part of the challenge is the management for the connection, and also handle the large number of high concurrent connections. But gRPC offers a very good feature that you can multiplex different connections from the same client, although like logically they expose to the user as different clients, but underlying they're using the same TCP transportation, actually HTTP transportation to the server. So that is reducing the number of connections by a lot and makes the connection load on server by a lot. And also because we can we use the thread, we can use the async, a non-blocking thread model on the server side. So we are able to serve a higher number of concurrent clients with much less resource used compared to what we do in the thrift. So with this, we have a high performance metadata performance, but also with the less effort to build this framework. But there are a lot more performance tuning, including the right. There are multiple, for example, there are multiple different threading models, threading pools, and we wrote we extended one of them and wrote a lot of extra logic into that. And also we tuned the buffer size, we tuned the like a thread pool, and also there's a lot of extra work required to make it really working well in this environment. So if you are interested, there's a link in the bottom to check out how our engineers document this, the lessons moving from Apache Thrift to gRPC. Okay, so that's so much for today for the topic I selected. I hope you learned something about how we build Alluxio. Hope we share some lessons in case you are doing something similar. But I'm also happy to answer your questions. I'm still learning how to use this panel. Let me know if you have problem to unmute yourself. So if you have any question regarding the talk I'm talking today or anything related to Alluxio, the technology or the community, I'm happy to answer. But first I need to figure out how to unmute you guys. Yeah, anyone to discuss any questions?
Hey, hello, Ben.
Yeah, hi.
Hey, so this is Song speaking. I work for VRite, and I have some question about the RAFT. So you're saying that from version 2.x that you guys begin to use your the RAFT to do the master election, right? So generally speaking, what's your recommendation for those high availability of the Alluxio masters? Do you recommend to use the new way or like the Zookeeper to do that?
Yeah. So here's my recommendation. First of all, you need to check whether you need high availability. So for a lot of cases, I know like for people running in EMR or data prog, and they're running Alluxio in the unfamiliar way. And in this case, they really don't need high availability because this is something only when you plan to run something to maintain Alluxio in a long running fashion that is required. Yeah, first check whether you really need HA. With HA, you are bring in more components, and more components means more complexity and more work to maintain. And second question is, okay, if you decided I really need HA, and then I will say like whether it depends on whether you have a Zookeeper and whether this Zookeeper is running well. If you already have a Zookeeper service and also have a shared storage like Alluxio can use, then the Zookeeper, the Zookeeper plus the shared storage as a journal storage is my recommendation way to go, because that has been practiced by so many users in many years. So I would say like that's more stable. And for the RAFT based journal, it's it's basically it's basically used more in the cloud-based environment because typically they don't have a shared storage and typically they don't have a zookeeper, and that's the case I would recommend to use the RAFT.
Okay, I think that in our environment that we're using those on-premise machines in the office. So in that case, what do you recommend? And because we noticed that sometimes of the Alluxio master, it's not that always achievable or not that always stable. So that is why we are trying to do those HA practice. So in
Yeah.
our situation, what do you recommend?
So you have zookeeper and you're running in your environment with like in a long running fashion, and you have zookeeper and HDFS, do you?
Not really. I mean, we need to set up the zookeeper,
Oh,
and in
okay.
our package we don't use HDFS in our office either.
Oh, okay. So in that case, then just use the RAFT based consensus protocol. Yeah. I think you're already running 2.2 if I remember correctly, right?
We try to run in 2.2, but pretty unfortunately, the 2.2 Docker image is not. I would say that the 2.2 version, the Docker image is not ready to run in the HA cluster, and I believe that one of my colleagues, Sheng, is already sent the exception log to the team members in Alluxio.
Okay. Um, I see. So for because in 2.2 we put the RAFT consensus RAFT based journal and data election as the default way to coordinate different masters. So if then you're running. So which version do you plan to run in the in the short term? 2.1 or 2.2?
I think that ideally I would prefer to use the 2.2 because that we know there's already a lot of those fixes we need, like the distributed loaded or something like that in the
Yeah.
2.2. So I
Yeah.
would use that if the 2.2 is stable enough, and especially that we want this one to be we want to use this one in the Docker version to for the maintenance purpose.
Mm,
That is why that we already tried 2.2, both 2.2 and 2.1.2
mm,
to run in the HA mode, but
mm,
looks like that right now only the 2.1.2 is I mean right now our setup is the 2.1.2 plus the zookeeper, but I would think that from your presentation maybe the 2.2 Docker version plus the RAFT is the I mean it's it will cause us less maintenance effort,
yeah.
and
Yeah.
hopefully it would more stable if it can run in the Docker version.
Okay. Yeah. So sounds like you yeah, I agree with your judgment, and I think that's going to be my recommendation too, using 2.2 and using Dockerize 2.2.0 in the environments. Seems like there is a blocker. You mentioned there are some issues running in your environment, running the Docker version in your environment, right? And you're already working out with team members. So I will say like let's work on that to make that clear. Make sure you can run 2.2.0 with Docker successfully in your environment, and then that will just introduce less issues of maintain. Okay.
Yeah, thank you.
Yep. Yep. Any other question?
And one more question from me again.
Yeah.
So this is Feng. So in our environment, we're thinking that whether, I mean, I'm not, I think that Alluxio is doing pretty good job in like if there's some cluster uh, only running, I mean, dedicated for Alluxio to work, and it's
Mm,
not like that dynamic size.
mm,
Uh, when I'm talking about dynamic size, meaning that there might be some workers join in and out. So my question is that in does Alluxio works well if, for example, sometimes some workers join and sometimes some workers out?
Yeah, I mean that depends. If you have data, if you only store read-only data in the Luxio, so you are not writing any new data into Luxio, or we call like in the cache terminology, you don't serve dirty data in Alluxio, then this should be no problem. But if you have dirty data which is not persisted into your under storage in Alluxio, then you may have the risk, you may run into the risk to lost data because you just decommission some workers with the data only on that worker. That's possible, right? So I don't know which case it is for you.
Yes, I get that meaning. But is it possible, or does Alluxio already support the situation that, for example, if I want to write the data, I only, for example, arrange part of my workers to do the write, which those workers are more stable workers, which will always be in the Alluxio cluster. Meanwhile, if we have other workers coming in and out, we can read from the other workers. So does Alluxio support those mixed mode?
Well, yes or no. The reason I'm saying yes is because we do have one data policy. You can specify a specific worker address. So okay, so let me take one step back. There are different policies you can set for Luxio to choose workers when you're writing new data to this space to Alluxio space. And by default, I think it's writing to local unless local is full or there's no local. So that's the default policy. And there's another policy you can set to write data to one specific worker. So I think what you need is a set of different workers. Like I need this policy to be able to always return this set of workers to write to, right? Rather than randomly pick one worker, which is another policy.
Does the policy apply in the master or apply in the client?
It doesn't matter actually. So as long as this is the client side or yeah, application side property, but as long as you set this in the master, this will be propagated to different clients as a default.
Great, get it.
Yeah, yeah. So sounds like to achieve what you need, we need to extend the policy a bit. Instead of having just one single worker accepting a list of workers to return. But I think that's possible. So can you create a GitHub issue, and I can maybe just take this. This is a simple enough task for me. Can just create a GitHub issue.
No. It's just some feature requests. Okay, the whole story looks like that because that we deploy those on-premise machine in our office. We just want Alluxio to work as a cache layer, right? So
Yeah.
we have some dedicated machine to run, for example, 3 machines to run the Alluxio master as well as the workers. Meanwhile, we also want to leverage engineers' daily workstation as some cache layer as well. So in that case, we would deploy the Alluxio worker into those machines. So that is why I'm asking that some of the machines, for example, in those 3 machines, they're stable. But for the other workers, they might be like in and out frequently. Not that frequently per se, it might be frequently in and out, for example, per several days. So in that situation, we might want to say that, oh, if you really want to something, you need to write into those 3 like stable workers. But if we want to read, try to read from the others first, or
Yeah.
try to write those stuff from all available workers. That is the whole story.
Yeah. Now I understand better. Okay, so in that case, maybe there's a way you can achieve this already, which is called tiered locality. I think that's a bad name, but it's kind of it's kind of like a confusing term. But essentially, what it does is it's dividing. You can divide your cluster into multiple different tiers. Yeah, dividing your cluster into multiple different tiers, and you can define this tier for the 3 workers you're running in the long running fashion as the first tier, and then you can set a data locality policy to I write data owning to this have at least one copy in the first tier. So I think that's possible. So I think that should be already achieved, supported.
Okay. What is the terminology again?
Tiered locality. Let me just ping you the link. I will ping you on Slack. So later on you can just retrieve this back. Okay.
Okay, cool. Thank you. That is very, very useful, I think.
Yeah. Yeah. Any other questions?
Hey, Sung, so do you have any questions?
So I'm searching the tiered locality. Okay, I find it. So okay, so I will ping you on Slack channel. You can just find it.
Thank you. And I believe that the colleague Sheng already sent an email to you, including those logs that the 2.2 cannot, the Dockerized 2.2 cannot work. So please keep us posted.
Yeah. Okay. I send it to the Slack general channel. By the way, for any other questions, feel free to just ask on the Slack channel, where so we can just engage. So this is the tier locality documentation. You can take a look. Okay.
Okay,
So
will
yeah,
do.
you just mentioned there's another email you sent it to me on the logs, right? Okay, I will take a look. Yeah. Yeah, any other questions from the other attendees, or feel free to introduce yourself, talking about your use cases, and I can provide some suggestions or recommendations, whether this is good fit or this is something you should maybe not pursue. Yeah, also, in the next few weeks, we have different online events set up. We will have one talk with Intel, talking about the latest work together to enable fast deep learning using Alluxio to in hybrid cloud cases. When I'm saying the hybrid cloud, it means really running computation in one place with the data in another different remote data center or different cloud or even the remote region. So Intel is working with us getting some benchmark work and also using their own deep learning, CPU-based deep learning framework called Zoo Analytics Zoo. So if you're running similar workloads, feel free to check it out. This is going to be in the April 23rd or 27th. I don't remember the date, but it's available. And also May next month, May 7th, we're co-hosting a tech talk with Facebook, talking about ongoing collaboration to reduce Presto latency by deploying a local version, a library version of Luxio to inside Presto to reduce the latency. So that's the ongoing work, developing work with Facebook. Cool. If there's no other questions, I will be hanging here for another maybe 5 minutes, but feel free to leave. And I'm also always curating on GitHub and also Slack channels. Our Slack channel is I will just send it to the chat, which is alluxio.io/Slack. And you can always go there to get an invitation, join our Slack channel, and talk to me. Cool. I found I'm just muted actually. I was talking about there's a Slack channel which is alluxio.io/Slack. You can get an invitation to join our Slack channel and talk to me. I'm always curating on both GitHub and Slack. Okay, that's so much for today. Thank you for joining this online office hour. We're on the cadence about two to three times a month. So feel free to join us next time and just watch out on our Slack channel. We will post the information of the next office hour. Thank you so much. Bye.
Bye bye.
Bye.